When we look out into the universe, our eyes are naturally drawn to the light. We map the stars, trace the galaxies, and chart the glowing filaments that make up the vast cosmic web. But the matter we can actually see occupies only a tiny fraction of the total volume of space. The majority of the universe is found in the dark, massive, empty regions stretching between those glowing structures. Astronomers previously treated these gaps as passive background noise, empty zones where nothing happens. We now know that these pockets of emptiness are active, dynamic forces driving the evolution of the cosmos. In 1981, astronomer Robert Kirshner and his team were mapping the 3D positions of galaxies when they encountered an anomaly in the northern sky. This animated diagram illustrates what they found: a spherical expanse of space roughly 330 million light-years in diameter. It dwarfs our entire local group of galaxies, the small cluster of nearby galaxies that includes the Milky Way and Andromeda. To see the scale of this desert, if the Milky Way were located in the center of the Boötes Void, humanity wouldn't have known that other galaxies even existed until the invention of deep space telescopes in the 1960s. Given the average distribution of matter across the cosmos, a region of this size should contain thousands of galaxies. Instead, researchers estimate there are only about 60 scattered across its entire volume. This massive absence of matter creates an isolated laboratory. It remains untouched by the gravitational pull of the wider universe, allowing us to test how cosmic structures evolve without external interference. Those 60 lonely galaxies that formed inside this vast emptiness offer a rare opportunity to see how matter behaves without outside influence. To study them, astronomers rely on integral field spectroscopy, or IFS. IFS is a method that captures a full color image and a detailed chemical signature for every pixel simultaneously, creating a 3D map of a galaxy's composition. In the crowded filaments of the normal cosmic web, galaxies constantly collide, strip each other of gas, and distort their shapes through gravity. Inside the Boötes Void, a galaxy sits undisturbed. The IFS data reveals that these isolated galaxies experience a delayed evolution. Because they haven't been forced to rapidly consume their fuel through collisions, they retain vast reserves of pristine hydrogen gas and younger stellar populations. They function as natural control groups, time capsules showing us exactly how a galaxy grows when left entirely to its own devices. Beyond the galaxies living inside it, the void also alters the light passing through its center, specifically the cosmic microwave background, or CMB. The CMB is the ancient residual heat radiation left over from the Big Bang. As a photon of this ancient light travels for billions of years across the universe, it eventually traverses one of these massive empty regions. This illustrates the integrated Sachs-Wolf effect. A photon loses energy entering a void, but regains it upon exiting. However, dark energy stretches and flattens the void while the photon crosses it. It exits with less energy, creating a measurable temperature drop, a cold spot. The void acts as a cosmic magnifying glass, projecting the invisible stretching of dark energy directly onto the oldest light in existence. A single cold spot could be a random fluke. To prove this energy drain was happening consistently, astronomers needed a much larger dataset. This sky map details the findings of a 2008 study. The blue circles highlight the locations of 50 different massive supervoids identified using the Sloan Digital Sky Survey. This image shows the stacked data from those regions. By averaging the microwave background temperature across all 50 supervoids, the bottom panel isolates a distinct temperature drop precisely where the voids are located. This result reached a statistical significance of over 4 sigma, meaning there is a 1 in 15,000 chance it was a mathematical error. This provided direct, physical evidence of dark energy. Researchers confirmed the existence of the universe's most powerful force by analyzing the places where there is absolutely nothing. The Boötes Void is an isolated incubator for galaxy evolution and a physical lens revealing the expansion of reality. Because of these discoveries, cosmology now focuses on mapping the entire architecture of space, including the vast regions where matter is absent. Modern observatories are now targeting these empty regions, using them to refine our models of gravity and expansion. To understand our origins and the ultimate fate of the universe, We must look past the light and learn to read the great nothing.